Angular velocity sensors, or tachometers, or tachos, are devices that give an output proportional to angular velocity. These sensors find wide application in motor speed control systems. They are also used in position systems to improve their performance. Velocity is the rate of change of position. Because the only components of velocity are position and time, extracting velocity information from two sequential position data samples should be possible, if you know the time between them. The math could be done with hardwired circuits or software. If the system already has a position sensor, such as a potentiometer, using this approach eliminates the need for an additional velocity sensor. Velocity data can be derived from an optical rotary encoder in two ways. The first would be to take the difference of two positions divided by the elapsed time. The second method involves determining the time it takes for each slot of the disk to pass. The slower the velocity, the longer it takes for each slot to go by. One popular method involves counting the cycles of a known high-speed clock for the duration of one slot period. The final count would be proportional to the time it took for the slot to pass. The optical tachometer, a simple device, can determine a shaft speed in terms of revolutions per minute, or RPM. As shown, a contrasting stripe is placed on the shaft. A photosensor is mounted in such a way as to output a pulse each time the stripe goes by. The period of this waveform is inversely proportional to the RPM of the shaft and can be measured using a counter circuit. Notice that this system cannot sense position or direction. However, if two photosensors are used, the direction could be determined by phasing, similar to the incremental optical shaft encoder. A toothed rotor tachometer consists of a stationary sensor and a rotating toothed iron-based wheel. The toothed wheel, which looks like a big gear, can be built into the part to be measured, for example, the crankcase of a car engine. The sensor generates a pulse each time a tooth passes by. The angular velocity of the wheel is proportional to the frequency of the pulse. For example, if the wheel had 20 teeth, then there would be 20 pulses per revolution. There are two kinds of toothed rotor sensors in use. One kind is called a variable reluctance sensor and consists of a magnet with a coil of wire around it. Each time the iron tooth passes near the magnetic field within the magnet increases, inducing a small voltage in the coil of wire. These pulses can be converted into a clean square wave with threshold detector circuits, as discussed in Chapter 3. The other type of sensor used for this application is the Hall effect sensor. The details of the Hall effect sensor are discussed later in this chapter. So for now, we will simply say that this sensor also gives a pulse each time an iron tooth passes by. A direct current tachometer is essentially a DC generator that produces a DC output voltage proportional to the shaft velocity. The output polarity is determined by the direction of rotation. Typically, these units have stationary permanent magnets, and the rotating part consists of coils. Such a design keeps the inertia down, but requires the use of brushes, which eventually wear out. Still, these units are useful because they provide a direct conversion between velocity and voltage. This figure shows the specifications of the CK20 tachometer. The housing of this unit is constructed so that it can mount piggyback on a motor, providing direct feedback of the motor velocity. The transfer function for the tacho has units of volts per 1000 RPM, or kRPM. We can use the transfer function to calculate the output voltage for a particular speed. Looking at the bottom of the figure, you can see that the CK20 comes in three models. For example, the CK20A outputs 3 volts for 1000 RPM, or 3 volts per kRPM. It has a speed range of 1 to 6000 RPM, so the maximum voltage would be 18 volts at 6000 RPM. This information can be displayed in a linear graph. From the graph, we can easily find out the output voltage for any speed. The linearity of the motor is given as 0.2%, which means that the actual velocity may be as much as 0.2% different from what it should be. For example, if the output is 9 volts, the velocity should be 3000 RPM. However, because 0.2 times 3000 RPM is 6 RPM, the actual velocity could be anywhere from 2994 to 3006 RPM. Velocities of thousands of RPM are much higher than you would normally find for actual heavy mechanical parts. Therefore, the tacho is frequently attached to the motor, and the motor is geared down to drive the load. As shown in this example, a motor with a piggyback tachometer has a built-in gearbox with a ratio of 100 to 1. That is, the output shaft rotates 100 times slower than the motor. The tacho is a CK20A with an output of 3 volts per 1000 RPM. This unit is driving a machine tool with a maximum rotational velocity of 60 degrees per second. What is the expected output of the tacho? And find the resolution of this system if the tacho were converted to digital with an 8-bit ADC as illustrated. A maximum tool velocity of 60 degrees per second can be converted to RPM as follows. 60 degrees per second times 1 revolution per 360 degrees times 60 seconds per minute gives you 10 RPM. Because of the gear ratio, the tachometer is turning 100 times faster than the tool. Calculating the overall transfer function of the velocity sensor, we find 3 volts over 1000 RPM times 100 RPM divided by 1 RPM gives you 0.3 volts per RPM of the tool. Now, using this transfer function, we can calculate that the tacho voltage would be when the tool is rotating at 10 RPM. So the voltage of the tacho is 0.3 volts divided by the speed of the tool times 10 RPM of the tool is 3 volts. To get the best resolution, we would reference the ADC to 3 volts, so that 3 volts is equal to 11111111, which is 255 in decimal. Because we know that the tacho is producing 3 volts when the shaft is rotating at 10 RPM, and that 8 bits represents 255 levels, we can calculate the RPM represented by each binary state. The resolution, the least significant bit, is equal to 10 RPM divided by 255 states, or 0.04 RPM per state. This means that the digital controller will know the shaft velocity to within 0.04 RPM. Therefore, the resolution is 0.04 RPM. That ends our brief look at velocity sensors.